Hi everyone, this is Mr. Cervone. Welcome to my math channel. In today's lesson, we will be learning about geometric constructions, specifically how to bisect an angle and how to draw perpendicular lines. So we will be learning 4 constructions in today's lesson pertaining to angle bisectors and perpendicular lines. The first construction is how to bisect an angle. The second construction that we will be learning, is how to construct a perpendicular to a given line and throw a point on that line. The third construction that we will be learning today is how to construct a perpendicular to a given line and throw a point not on that line. And finally, our fourth construction will be how to construct a perpendicular bisector of a given segment. Now, for each of these constructions, we will also justify or prove why these constructions work. As a matter of fact, in this unit, for constructions and also on the Regents exam, you also need to justify why each construction works by stating any of the theorems or postulates or definitions in form of a paragraph proof or a statement reason table. But we will learn it in today's lesson. So without further ado, let's get started with the first construction, how to bisect an angle. Okay, so in this particular example, we will be looking at how to bisect an angle using a compass and a straight edge. So let's get started. So the first thing you want to do is to draw the angle. So we're drawing 2 rays here like that, such that they intersect at some vertex point. So let's call that vertex point A, and let's draw the arrows as well to show that these are rays. So the next thing we want to do here, since we want to bisect this angle, is to first construct an arc such that the arc intersects both rays. Okay, so we want to open the compass, not too narrow or not too wide, but in a way that we can still draw a nice arc here, nice and neat. Okay, and let's call these points of intersections B and C. It's always good to call these points of intersections some letters so we can always refer to them, especially during a proof. Now, what we want to do next is to select another width, or we can even keep the same width, it doesn't really matter. But let's say we pick this particular radius here on the compass. We want to put the compass on B, and we want to draw an arc in the center here, okay? So the arc has to be big enough that we can draw it approximately where we think there's going to be the angle bisector located. Now we're going to keep the same exact radius or width on the compass, go on C, and draw another arc here, okay? The most important thing here is that both of these arcs need to be intersecting at some point, let's call it point D. And another important thing is that both have the same radius. So basically, if, let's say, measure the distance from C to D, and we measure the distance from B to D, then it will turn out that these are actually congruent, and that will be used for the proof as well. So the last step is to simply connect A to D and then extend it and draw the arrow. So now it turns out that we actually bisected this angle. So why does this work? Okay, so let's look at the proof now. So after viewing the video, let's now discuss why this construction works. And as a matter of fact, it can be proven that ray AD is indeed the angle bisector. So let's actually prove it now. So the first thing to do is to set up a statement reason table, and then we think, okay, so what are we given here and what we're trying to prove? So it turns out that here we're given angle BAC, okay? Now, when we drew the arc that connects B and C, what can we notice here? Well, we know that the segment AB and segment AC must be congruent. And why they're congruent? Because these are the radii of the same circle. So let's write that in. So here we can say that segment AB is congruent to segment AC because radii of the same circle are congruent. Now after that, we constructed the arc that connects the radius from B to D and the arc that connects the radius from C to D. And it turns out that those radii are also congruent because they're from congruent circles. They're not from the same circle, but we did not change the width of the compass. So let's write that in. So segment BD is congruent to segment CD because radii of congruent circles are congruent. So let's denote that also in the diagram, that we have this segment congruent to this segment, and there's another segment that is congruent to the segment of itself, which is segment AD. So let's write that in. So segment AD is congruent to itself because of the reflexive property, so we can denote that in the diagram. And as we can see here, we have triangle ABD and triangle ACD to be congruent to each other. And the reason why these triangles are congruent is because of the SSS postulate. Now, since the triangles are congruent, we can say that the corresponding parts are congruent. Namely, angle BAD is congruent to angle CAD. And we can denote that in the diagram as well. So we have these two angles to be congruent. And the reason is, again, corresponding parts of congruent triangles are congruent. So what that means is that ray AD is now an angle bisector. So now we can write as step number 7 that ray AD bisects angle BAC because that is the definition of an angle bisector. And that's basically how we prove the first construction. Let's now look at the second construction. Basically, the second construction is how to construct a perpendicular to a given line and through a point on that line. So let's watch that video now. So in this video, I'm going to show you how to draw a perpendicular through a point on a line using a compass and a straight edge. So the first thing you want to do is to draw a line here using a straight edge. So let's also label the arrows here on the right and the left. And now we want to specify a point on the line. Let's call it point P. And our goal is to draw a perpendicular through that point that is perpendicular to the line. So how do we do that? Well, it's basically the same concept as bisecting the angle, because in this case, we're just bisecting a 180-degree angle. And so we want to take our compass here, put it on point P, and then select a width such that we can draw arcs that intersect the line on both sides. It is possible to draw the entire arc, but aesthetically it will look nicer if we just draw two arcs, so we have more space on this side to draw or to construct the other arcs. Okay, so the most important thing is that these two points of intersections here, so let's call them points A and B, are equidistant to point P. Okay, so that's really the key here in also proving why this works. So the next thing we want to do is select a width from B to P or from A to P that is more than half of the distance from A to B. Okay, the reason why we want a distance that is more than half is so that we can draw an arc above where the approximate perpendicular is going to be drawn, and then we keep the same radius or the same width and put the compass on A and draw another arc here. So the most important part of this is that both arcs must intersect at a point, let's call that point C. So at this point, all we need to do is connect point P to C and extend it, and it turns out that now this line here is going to be perpendicular to the given line. So here we can say that line L is perpendicular to K. So if we had to prove this, we can think of the following. Here we're given line L and point P, okay? How would we prove that line L is perpendicular to line K? So, and the key here is to really understand that AB or AP here, segment AP is congruent to segment BP. So let me highlight that in the diagram. And also when we drew the arcs here, that these two segments represent the radius of that circle, and these are also congruent. Okay, so we can say that segment AC is congruent to segment BC. Okay, so how would we prove that these two lines are perpendicular? Okay, so after watching the video on how to construct a perpendicular to a given line and to a point on that line, let's discuss how we can prove this. And as a matter of fact, we're given that we have line L and point P on line L. How do we prove that line L is perpendicular to K? To get started, let's set up a statement reason table. So here's the statement reason table with the first given, which is line L and point P on line L. So let's think about this. What is the first thing that we did? Well, we constructed arcs such that they intersect at points A and B as shown in the figure here. And we can actually say that segment AP and BP must be congruent because radii of the same circle are congruent. So let's write that into the statement reason table now. Okay, so now that we have step 2 in the statement reason table, what else can we write here? Well, if we think about what else we constructed the arcs, one from the right side with the center at B all the way to point C, and another arc with center A all the way to point C. So it turns out that segment AC and BC are also congruent because radii of congruent circles are congruent. So let's write that in. Okay, so what else can we do at this point? Well, if we look at segment PC or CP, doesn't matter, we can say that it's congruent to itself. And we know that is true because of the reflexive property. And again, we can now prove the triangle's congruent. Here we can say that triangle ACP is congruent to triangle BCP because of the SSS postulate. Since they're congruent, the corresponding parts are congruent, namely angle APC congruent to angle BPC, because corresponding parts of congruent triangles are congruent. Now, if we look in the diagram and we know that these two adjacent angles are congruent, right? They're congruent and adjacent. Therefore, they must be perpendicular. And there's a theorem that justifies that. So here in the statement reason table for step number 7, we can finally say that line L must be perpendicular to line K, because if two lines intersect to form congruent adjacent angles, then the two lines are perpendicular. And that's basically the proof for the second construction. Let's now look at our third construction, how to construct a perpendicular to a given line and through a point not on that line. So let's look at that. So in this particular example, we want to draw or construct a perpendicular through a point not on the line now in this case. So let's first draw a line. Let's call that line L, and let's draw a point that is not on the line, which is outside, and let's call that point P. Okay, so the goal here is to draw a line that goes through P and is perpendicular to L. How do we do that? Well, first we take our compass and we put the center of the compass on P and select a width or radius that goes actually beyond the length from or the distance from P to line L, okay? Notice that any distance is always perpendicular in geometry. So then we want to draw or construct an arc such that it intersects line L at two different points. Let me label the points as A and B, okay? So what do we know so far? Well, since here we know that this is a radius and this is a radius, so we know that segment AP and BP must be congruent because radii of the same circle are congruent. So the next step is to select a width now that is approximately half or more than half the distance from A to B. And then we want to draw an arc on the right side and one on the left. Basically one from A and one from B. But the most important part is that they have to have the same radius. So let's call that point C, okay? So again, what do we know here? That this segment here, AC, is also congruent to segment BC. Okay, so the next step is to connect P and C and extend these and label these as a line. Okay, so what we just did is construct a line that is perpendicular, so let's call that line K, perpendicular to line L, and it goes through point P, which is not on line L. Okay, so again, we want to prove this. Why does it work? So again, we want to write the following: given line L and point P, again, point P is not on line L, how do we prove that line K is perpendicular to line L? So let's discuss this now. So after viewing the video on how to construct a perpendicular to a given line and through a point not on that line, how do we prove it? How do we know that line L is always going to be perpendicular to line K? Similarly, we want to also here set up a statement reason table. So let's look at the statement reason table now. So in the statement reason table, the first statement is line L and point P not on line L, which is the given. Then what have we done afterwards? Well, from point P, we drew the arc through point A and B as shown in the figure. And it turns out again that segment AP and BP are congruent. So for statement number 2, we write AP, or segment AP, congruent to segment BP because radii of the same circle are congruent. What do we do afterwards? Well, afterwards, we constructed the arcs from point A and from point B such that those arcs intersected at point C. And those are radii of congruent circles. So let's write that in as step number 3. Okay, so here we have AC congruent to BC, those segments, because radii of congruent circles are congruent. Now, we can also say that segment PC is congruent to itself and then prove the triangle's congruent. So let's do that. Okay, so now we can state the following in the statement reason table: that triangle ACP is congruent to triangle BCP because of the SSS postulate. Now, when two triangles are congruent, that allows us to state that these two corresponding parts or angles must be congruent as well. So let's write that in the statement reason table. Okay, so angle APC congruent to angle BPC because corresponding parts of congruent triangles are congruent. And now, if we add a point D where segment PC and AB intersect, we can actually prove triangle APD congruent to triangle BPD. And we will know why in a bit. So let's do that first. First, we write that segment PD is congruent to itself, and then triangle APD is congruent to triangle BPD because of the SAS postulate. Now, what does that allow us to state? Again, that these two adjacent angles must be congruent, okay? So here we can say angle ADP congruent to angle BDP because it's the same reason as 6 corresponding parts of congruent triangles are congruent. And finally, we can state that line L perpendicular to line K because if two lines intersect to form congruent adjacent angles, then the two lines are perpendicular. So now let's look at our final construction. So let's see how to construct a perpendicular bisector of a given segment. So let's watch the video. Finally, we want to construct a perpendicular bisector of a segment. So first, let's draw a segment and let's call the endpoints A and B. And our goal here is to draw a perpendicular line and bisect that point at its midpoint, or bisect the segment at its midpoint. So we take our compass, put the center on A and select a width that is more than half of AB. So that's important so that we can get some arcs of intersection here. And we want to draw an arc on top and one on the bottom as shown, okay? So now we keep the same radius, put the compass on B, and draw the same arcs. And it's very important that these arcs intersect on the location above the line segment and location below the line segment. So if we call these points of intersections C and D, then we can simply connect segment or connect point C and D such that we end up with a line that is CD. And it turns out that this is now perpendicular and these segments are also congruent. Okay, so again, let's say we're given segment AB. Okay, how do we prove that? First of all, so let's write number 1, that line CD is perpendicular to segment AB. And secondly, let's call that point M. How do we prove that M is the midpoint? M is the midpoint of segment AB. So let's discuss this now. Okay, so after watching our last construction on how to construct a perpendicular bisector of a given segment, let's prove it now. Again, we set up a statement reason table and post the first given. Okay, so after we posted our first given, let's think back what we did first. So from point A, we selected a width that is more than half of segment AB and constructed an arc going through point C from both sides. So it turns out that all these segments that are drawn now in the figure, they're all congruent. So let's write that in the statement reason table. So here we can say that segment AC is congruent to segment BC, congruent to segment AD, and congruent to segment BD, because radii of the congruent circles are congruent. Now, what kind of shape is this now? A, C, BD. It actually turns out that when all the sides of a quadrilateral are congruent, then we know for sure that it is a rhombus. We don't know if it's a square, but for sure we know it's a rhombus. So let's write that in. Okay, so here we have ACBD is a rhombus because that is the definition of a rhombus. As we remember a while ago, the definition is a rhombus is a quadrilateral with all sides congruent. Okay, so let's think about the properties of the rhombus. Here we know that segment AB and segment CD are the diagonals of this rhombus. What must be always true about the diagonals? That the diagonals are always going to be perpendicular. So let's write that in. So here we have for step number 4, line CD is perpendicular to line AB because the diagonals of a rhombus are perpendicular. So that's basically the first part of the proof. How do we know that M is the midpoint of segment AB? Well, what else do we know about diagonals? We know that they bisect each other. So let's write that in. So first we write that line CD and line AB bisect each other at point M because the diagonals of a rhombus bisect each other. And then we can say that point M is the midpoint of segment AB because that is the definition of a segment bisector. Therefore, we can say now for step number 7 that line CD is the perpendicular bisector of segment AB because that is simply the definition of the perpendicular bisector. And how do we know that? Because first we stated that CD is perpendicular to AB. That's the perpendicular part here. And then the other one, let me use a different color here. We have that M is the midpoint. Okay, so M is the midpoint of AB. So that is basically the bisector of segment AB. And that's basically it for this particular proof, for this construction. That's also it for today's lesson. Again, thank you for watching and have a wonderful day.